Hello class, and thank you for watching. In topic 1.8, rational functions and zeros, you will learn to determine the zeros of a rational function and also solve inequalities, rational inequality situations. Let's begin by looking at how do we identify the zeros and the domain of a rational function. Well, since a rational function is the quotient or the ratio of a numerator function and a denominator function, n of x and d of x cannot have a common factor. So there can never be any common factor among them. Now r of x has a 0 whenever the numerator function is equal to 0 and the rational function is undefined when the denominator function equals to 0. This second part right here tells us what the domain of our function is. And it's going to tell us exclusively what numbers are excluded from the domain. So for whatever values of x, whatever number, okay, that makes the denominator equal to 0, we'll call that c, all right? X cannot equal to the values of c where the denominator function at that value of c equals to 0. And that's how we identify the domain. Our domain would be all of the values except for any number that makes any number c that makes the denominator equal to 0. So let's find those. Let's find our zeros when we're going to cross the x-intercept, and let's find the numbers that are restricted from the domain. So let's look at example number 1. To find the zeros, I'm simply going to look at my numerator function, x minus 2, and set that equal to 0 and solve this equation. Well, this is a simple equation. I add 2 to both sides. So x equals 2. That is my 0. My 0 is going to be the number 2, that x is equal to 2. Now, to find the domain of this function, I'm going to look for the values of x that make the denominator function of this rational function equal to 0. So I'm going to look at the denominator and see what makes that equal to 0. So x plus 6 and x minus 3. Well, what makes this equal to 0? Well, to make the first factor equal to 0, x would have to be negative 6. And to make the second factor equal to 0, x would have to be positive 3. So for this example right here, our domain is going to be all of the x values with the exception of these two numbers. So x cannot equal to negative 6, nor can it equal to positive 3. That's going to be our domain. Meaning that we can pick any number that we want for x with the exception of those two. So just to, again, make sure that you understand this. This right here, what I'm saying that x cannot equal to these two values, mean that x could be any number that I want. I can plug in any number that I want right here except for those two numbers. Because as soon as I plug in any one of those two numbers, the function doesn't have a value. We have no y value to this equation. And I'll show you just on this one example right here. So if I plug in the number 6, I end up with 6 minus 2 in the numerator. Negative 6 plus 6, and negative 6 minus 3. On the top, I have no problem. That's equal to negative 8. But on the bottom, I'm going to end up with 0 in the first parentheses and negative 9 in the second parentheses. And well, I cannot divide by 0. This is where the problem comes in, okay? Negative 8 divided by 0 is undefined. This, again, y value is undefined when x equals negative 6. So since this doesn't have a y value when we plug in this number, that means that this number right here cannot be a number in the domain. It cannot be a coordinate on the graph. So we have to exclude that number. And the same thing is going to be true with the 3. The only difference is that this will then end up being a 0 when I plug in the 3 right there. But I'll end up with the same situation. A different number on top, obviously, but I'll still be dividing that number by 0, which again is does have no value. So our domain is this. So we'll say that x cannot equal to that, which means again we could plug in anything else except for those two values. Let's get the next example. So for this example right here, let's figure out what the zeros are. So our zeros are going to be where the numerator is equal to 0, so x minus 1 times x plus 2, and there's two of them because it's to the second power. When is this going to equal to 0? Well, x is going to equal to positive 1, and x is going to equal to negative 2, a total of 2 times. And obviously I don't have to repeat this because it's going to be the same number. So here are the zeros. X equals 1 and negative 2. Negative 2 just has a multiplicity of 2. Now let's find the domain. Or our domain would be when the denominator function x minus 2 is equal to 0, and well, our denominator will equal to 0 at positive 2. So that's the number that we're going to exclude. So we're going to say that the domain can be anything except for that value. So x cannot equal to positive 2. Let's now move on to the next example. So the same thing here. To find the 0, we're going to get 4x plus 8, the numerator function, and set that equal to 0. This equation requires us to subtract 8 from both sides. We will then divide by 4, and negative 8 divided by 4 is negative 2. Now to identify our domain, we're going to get the denominator function and set that again equal to 0. So the first one, x would have to be negative 5 to make the first factor equal to 0, and x would have to be negative 2 to make the second factor equal to 0. So our domain would exclude those values. So x cannot equal to negative 5, and x cannot equal to negative 2. Now let's look at example P. Example D, function P. So for this one, to find the zeros, we're going to get our quadratic or our numerator function, x squared minus 4, and set that equal to 0. Now these are not linear factors because we have x to the second power. So what we're going to do is we're going to factor this out. So let me do that first. Notice that these are not linear factors. This is x to the second power, not a line. So we're going to break this up and factor the x squared minus 4. That can be broken up because of the difference of squares as x plus 2, x minus 2. Simply take the square root of that, and of course split that into 2, x and x, and the square root of 4 is 2 and 2, and we just add 1 and subtract the other one. That's the difference of squares. Now let's factor the bottom one first before we find the zeros in the domain. Since this is not a linear factor, it's not in the factor form, we'll factor this by splitting this up to x and x. This is negative and negative, and the factors of 25 that give us 10, with both of them being negative, is going to be 5. 5 and 5. So there. Now that I have the linear factors, now I'm going to find the zeros. So we have an x plus 2 and x minus 2, and we're going to set that equal to 0. And x is going to equal to negative 2 and positive 2. So those are the zeros. And now for our domain. X minus 5, and well, it's 2 of them, so I just have to do it one time. I really don't need 2 of them because it's the same factors, x minus 5 times x minus 5. So x will equal to positive 5. So that's the number that we would restrict. So our domain cannot equal to that positive 5. So that's our domain. X cannot equal to positive 5. It could equal to anything else, which again, what this statement's saying is that it could equal to anything else. So you can pick any number from negative infinity to positive 5, and then 5 to infinity. In interval notation, we will represent the interval like this. Using a not equal sign, they would look like that. Let's look at the back now. And now let's use this technique and how we find the zeros and the restrictions in the domain, those numbers again that we can have the denominator equal in order to solve inequalities, okay? So to solve a rational inequality, we're gonna first start by making sure that the inequality has a zero on the other side, specifically on the right side. We want to look at this where our inequality is on the right side. The zero, I'm sorry, is on the right side of the inequality. Then making sure that you have a single rational function in factored form. That in factored form, we're going to find again where the numerator is equal to 0 and where the denominator is equal to 0. So again, we're going to identify both the zeros and the undefined values. And we're using those numbers, we're going to create a sign chart, just like we did with the polynomials, with the values that we got from this step right here. Now, be careful to mark the values again of d of x so that we never again include those values in the solution. So remember, when we have inequalities, we have two options. We can include the zeros, okay, because of the equal sign, but because these are the values where the denominator is equal to 0, those numbers again get excluded from the domain. So we have to make sure that we never include those values in the intervals. And then we just do the same technique as before. We're going to test values in each interval to see if the value are positive or negative, and we're going to interpret the sign chart to answer the given inequality from the problem. Now again, be sure to write your answer in interval notation, and again, think about the endpoints, okay? Make sure you think about the endpoints. So let's look at this example right here. So first of all, it's already in the factored form. So let's first find the zeros. Where is the numerator x minus 2 going to equal to 0? X minus 2 is equal to 0, where x equals to positive 2, okay? So we're going to use this number in a bit. Then we're going to look at where the denominator is equal to 0. So starting with x plus 6 first, where does x plus 6 equal to 0? That's going to be at negative 6. And then the last one, x minus 3. When does x minus 3 equal to 0? And that's going to be at positive 3. Now, this one right here, again, is a 0. I'm going to highlight my 0 in yellow. Okay, this is very important. And I'm going to highlight the restrictions in the domain in red. Again, so x cannot equal to these two numbers right there, okay? So when we create our number chart right here, I'm going to highlight these restrictions in the domain in red. So from least to greatest, from negative infinity to positive infinity, we're going to go negative 6, positive 2, and positive 3. I don't know why I make these things so long. These things do not have to be that big, okay? And all we're going to do now is just simply test, again, test the values that fall within that boundary, okay? So at between negative infinity and negative 10, I'm going to start by testing the number and testing negative 10, okay? So what I'm going to do, again, using my rational function, I'm going to plug in this negative 10 into these x values and see if I'm going to end up with a positive number or a negative number. So if I plug in negative 10 here, that's going to end up giving me a negative value. Negative 10 minus 2 is negative. And then when I plug in a negative 10 on the bottom, a negative 10 plus 6, that's going to be a negative 4. And a negative 10 minus 3 is going to also be a negative number. So I'm testing that value here, okay? So I'm starting with that. I'm testing that. Now, the rules again are the same with multiplication as they are division. An even number of negatives become a positive, and an odd number of negatives become negative. So right here, since I have no positives, again, I don't have to worry about that. I have to worry about how many negatives I have. Since I have an odd number of them, only 2 of them can pair up to become a positive. So this one negative sign that doesn't pair up makes the entire thing negative. So in this interval, we are going to be negative. Now, I forgot to do this again at the beginning. These again are my restrictions on the domain. So these endpoints are never going to count and are always going to be excluded from the intervals. So I need to make sure that I label those, okay? So there. Now, let's test another number. So we're now going to test x equals, let's say, a number between -6 and 2. Well, the easiest number is 0. 0 is found there. So let's see what happens when we plug in 0. So if I plug in 0 in here, 0 minus 2, that's going to be a negative value. 0 plus 6, that's going to be positive. And 0 minus 3, that's going to be negative. And again, look, I have an even number of negatives. So these 2 negatives become a positive. And no more negatives means that the entire thing is positive. So this right here is going to be positive. Now, let's test another number. Let's now test x equals between 2 and 3. Let's test the middle number, 2.5. So 2.5 minus 2, well, 2.5 is bigger, so 2.5 minus 2, that's going to become positive. 2.5 plus 6 is positive. But 2.5 minus 3, 3 is bigger. As you see right here, it's in the middle. So getting this number, subtracting it by 3 is going to make it negative. So negative. And look, only one negative value that doesn't pair up with anything, so that's going to make everything negative. So everything is now negative. And now we can look at 3 to infinity. So let's try positive 10. And I probably should have split this up already. Okay, so now let's test positive 10. So if I plug into 10 minus 2, that's positive. In the bottom, it'll be 10 plus 6, which is positive, and 10 minus 3 is going to be positive. No negative signs here, so everything is positive. So there. Now, the question is asking us, when is this inequality going to be greater than or equal to 0? Well, it's greater than 0 on the plus side, okay? So here and here. Now, because it equals to 0, we can include, again, the zeros. Not the restrictions on the domain, but the zeros. The only 0 I have is 6. So the only number I'm allowed to include, okay, is going to be this one right here. Everything else is supposed to have a parentheses, and the only number that's going to have a bracket is the number 2. So on the interval here that is positive is from 6 to 2 and 3 to infinity. So the interval would be from -6 to 2 and from 3 to infinity. Now, why is the 2 again? Let me emphasize this. Why is 2 the only one that has a bracket? Is because that's the only 0. That's the only place where this entire thing is going to equal to 0. The top one. At these bottom places, when we equal it to 0, those are the numbers that get restricted from the domain. So these are the numbers that if I plug them in, make these again undefined. It gives me that the y value doesn't exist. So I cannot include those numbers that get restricted in the domain, even if we have that equal sign there. So the correct notation would be this. This is where the solution to the inequality. Our rational function will be greater than or equal to 0 between -6 to +2, close parentheses on the 2, and then 3 to infinity. Let's look at the next example. Let's look at example number 3 now. So for this one right here, before I can start doing this, I need to make sure, I need to factor this. So I need to factor both the numerator and the denominator. So to factor this, because it's a difference of squares, that's going to be x plus 2, x minus 2. Now to factor the denominator, do green. To factor the denominator, we're going to break up the x squared to x times x. So x times x. Negative 10x plus 25. Well, we just did that one in the previous example. X minus 5, x minus 5. And it has to be less than 0. Okay. So now let's look at where our zeros are. Our zeros is going to make this equal to 0. So that would be a negative 2. And it will be whatever makes this equal to 0. Well, that's going to be a positive 2. And for the domain, the values that make this equal to 0, the numbers that get excluded from our function, are going to be positive 5. So x cannot equal to positive 5. So using those three numbers, we're going to make a number line plotting those points from negative infinity to positive infinity. So negative 2, positive 2, and positive 5. So now there's 4 intervals, so let me break this up into 4 places. We're going to test 4 different numbers. So test 1, test 2, test 3, and then test 4. Again, 4 intervals in between those, 2, 3, and 4. So let's do it on the very far left. Let's start by testing negative. Oh, the negative something come on. So let's test negative 10. And again, we're going to use the factor form. Now that I have it factored, we're going to use this instead of plugging it up here. Remember, this and this are the same. So let's plug it into the factor form. So as you can see, again, you have to make sure that you factor correctly, because any one of these factors that's wrong, then the entire thing is going to be wrong. So always, again, factorization is very important, which is why we practice it so much, again, the last week. So if I plug in negative 10, well, a negative 10 plus 10, that's going to be negative. A negative 10 minus 2, that's going to still be negative. And now for the bottom, a negative 5 minus 10, or negative 10 minus 5 is going to be negative, and well, the same thing on the other one, negative. Now we have an even number of things, so this is going to be positive, and we're going to be above the x-axis on the first interval. Now let's test a number in between negative 2 and positive 2. Well, let's test 0. 0 is in between. Anytime we change from a negative to a positive, 0 is there. So let's test 0. So 0 plus 2 is positive. 0 minus 2 is negative. 0 minus 5 is negative. And again, 0 minus 5 is negative. Since I have an odd number of negatives, one of them is not going to pair up with something, so the entire thing is going to be negative. And now let's test x equals positive 3. We'll do 3. We could do 3 or 4. Let's do 3. 3 plus 2 is positive. 3 minus 2 is positive. 5 minus 3 is negative. And well, again, negative. 5 minus 3 again is negative. An even number of negatives, so that is going to be positive. And now finally the last one. So let's test positive 10. So let's see what happens when x is equal to positive 10. 10 plus 2 is positive. 10 minus 2 is positive. 10 minus 5 is positive. And 10 minus 5 is positive. So no negative sign, so everything is going to be positive. So where are we going to be less than? Oh, and I didn't highlight these. I always need to remember to highlight this. Again, this number at 5, we can never include that one. So we always make sure that we highlight that one or put a little circle somewhere, again, to indicate that we cannot equal to that value. So here for this example, when is our function less than 0? Well, that's going to be in the negative interval. So from -2 to +2. And since we're not equaling, again, to those zeros, we're going to use the open interval, -2 to +2. So there's your solution. Now, pay close attention to these two, the difference between these two examples. Notice that on the example on the left, example 2, we alternated. We started at negative, positive, negative, positive. It was alternating. But on this one, it started to alternate positive, negative, positive, but then it stayed as a positive. It didn't turn to a negative, meaning it didn't move below the x-axis. Well, if you look at the reason why, the reason for why is that x cannot equal to 5 a total of 2 times. The multiplicity, again, of this number that gets excluded from the domain is an even number of times. So not only can x not equal to 5, but it cannot equal to 5 an even number of times. So the graph behaves again accordingly, like if it was actually connected and be tangent at that location. The only difference is that we're not going to be tangent here. Okay, so that's not the right way of describing it, because we do not touch the x-axis there. At 5, there is no solution. But because we have 2 of these places, the graph doesn't change and it just simply stays above. Again, it's not tangent. If I graph this, as I'll show you tomorrow, it's not tangent, but it does stay above the x-axis at that location. Everywhere else it's alternating, and at that place, since it was positive on the left, it's going to be positive on the right because the multiplicity was an even number of times. Let's look at this next example right here. So to solve this one, well, the numerator, again, to find the zeros, this is already in factored form. There is no zeros in the numerator. There's no way to get 2 to equal to zeros. So none, okay? No zeros at all. And for our domain, well, what's going to make this one factor equal to 0? Well, that would just have to be +3. So x cannot equal to +3. So there's only one place we have to look at. And again, this number does not get included. So let me make sure I highlight it in red and right here to remind myself, okay, I do not include that point. Let's see what happens. We're looking for where this is going to be greater than 0. And you know what? Let's leave it like that. Okay, greater than 0. So let's see what happens. So there's only 2 places to test. So we're going to test only 2 locations. We're only going to have 2 tests. And we'll start with testing to the left of 3. So 0 is on the left of 3. And on the top is going to be positive because there's no number to plug in right there. So that's going to just be +2. Okay. But what about on the bottom? Well, if I plug in 0, 0 minus 3 is negative. So this does not simplify to positive because the negative sign doesn't pair up with anything. So we're going to be negative on the left side of 3. And now we have to test a number on the right side of 3, so we'll test 4. Again, +2 is going to obviously stay as +2, but this time 4 minus 3, that's equal to a +1. So we're going to end up with positive over positive, so this is positive. So when is our function going to be greater than 0? Well, that's going to be where it's positive, so from 3 to infinity. So our answer is the interval from 3 to infinity. And this one I didn't have to worry about including because it was going to be strictly greater than, so I didn't have to worry about including again anything. So everything was automatically going to be open intervals. And now let's look at the next example. So for this example, it's already in the factored form. X minus 1 means we have two of those. So just remember we have two. So let me rewrite this as 1 over x minus 1 times x minus 1. I said x minus 2 earlier, but I meant x minus 1. We have two of these x minus 1s. And we want to know when is this going to be greater than or equal to 0. So the first thing we need to do is find the zeros. Well, since it's the number 1 on top, it doesn't have any x's on top here. There are none. There's no way to get this thing to equal and touch the x-axis. Now to find our domain, our restrictions are where the graph is not going to have a value. Well, we cannot have a value at positive 1. Because if I have x equal to positive 1, then this doesn't work anymore. This doesn't exist. It doesn't have a value. So our domain will be everything except for 1. So using that one number only, we're going to break our number line exactly like the last one. But again, since this is the number from the domain, we're not going to include that number. And since there's only two intervals, we're going to only test two numbers. So let's test negative 10 and we'll test positive 10. So if we plug in negative 10, the top is obviously going to be positive 1. And on the bottom, negative minus 1, that's going to be negative. And again, there's two of them, so negative, negative. So again, negative 10 minus 1 and negative 10 minus 1 is negative, negative. And again, these pair up to become positive and no more negative. So the entire thing is positive. Now for this one right here, x is going to equal to 10. So 1 is obviously going to be positive, and 10 minus 1 is going to be positive, and 10 minus 1 again is positive. So everything is positive, so positive. So when is this thing going to be less than 0? Never. It is never less than 0. When is it going to be equal to 0? Well, never. There are no zeros, okay? So it's never going to equal to 0, so this has no solution. Okay, or better yet, D and E. The interval does not exist. So we'll write this if we come across something like this on our assignment. Okay? Now, let's talk about this last example, example number 4, just one more time. Had this had an equal sign, the answer would not change. Because the answer is asking, when is this thing going to be greater than 0? Well, we're going to be greater than 0 from 3 to infinity. And when is it going to equal to 0? Well, never. There are no zeros. We never equal to zeros. So it can never equal those values. So our interval is not going to change, even if it has an equal sign there. Let's now move on to the last page and let's look at this example right here, okay? So we finally have a picture to represent again what's going on at these values that the domain restricts. So at these locations where x cannot equal to those values, there are what are called vertical asymptotes there. There are these boundary lines that the graph does not cross. That's one option. The other option is that there could possibly be a hole in the graph at that location. And we'll distinguish the differences between those two in a later section. So for this example right here, the graph of the rational function f is shown in the figure above. Use the graph to solve the following inequalities. So at these locations right there, these vertical lines, these are the numbers that are restricted in the domain. So x cannot equal to -3, nor can it equal to +3. And well, from the previous lesson, you should be familiar with this. This right here is our horizontal asymptote. So the left end behavior is approaching, again, this horizontal line of 1 and +1. So even though it's not asking us to do anything like that, let's write this down. That the end behavior on the left side of this function f is positive 1, and the right hand behavior of f is also equal to positive 1. Okay, and I'm just adding that because, again, just to review what we talked about yesterday. Now let's go into the question. Okay, so here we have this graph of f, and they want to know, when is the graph of f going to be less than or equal to 0? Less than or equal to 0 simply means that we have to be below, let me highlight it in yellow instead, below this line right here, or touching that line right there. Less than or equal. Let's first find where it equals to 0. Well, it equals to 0 at these two blue locations. So x is equal to -1 and x equals to positive 2. When are we going to be below that yellow line? Well, if we look at the portion of the graph, we are below that yellow line. This portion of the graph is below that yellow line, which is between the x values. Let me do that in purple. Between this vertical line here and that blue point there. So from -3 all the way to this blue point where the x value is -1. So between -3 and -1. Where else are we below that yellow line? Well, right here. This portion of the graph is below that yellow line, which is in this little region right there, which goes from +2 all the way to this vertical line right here, which is at +3. So from +2 to +3. Now it's asking us, so that's when it's going to be again, I'm going to put parentheses, oh no, not yet. And that's what it's going to be below the x-axis. Well, when does it equal to 0? When does it equal to the x-axis? Well, it equals to the x-axis at -1, so we have to put a bracket around -1, and it equals to the x-axis at +2. So here we have +2, we're going to put a bracket right there. It doesn't equal to 0 at -3 and +3, as you see right there. We're not touching the x-axis at those locations. So we're going to put parentheses around that, which is exactly what happened in this situation. If I go back to the previous page, which is exactly what's happening right here in this example right there, okay? This is the point where we're touching the x-axis at 2. At these other locations, there's these imaginary vertical lines that the graph again is skipping over, and it's a boundary, it's a vertical boundary line that the graph doesn't ever touch, like in this example right here. So the answer to this is going to be this. This is the interval where our function is less than or equal to 0. And of course, the union in the middle. Now, when is our function greater than 0? So when is it going to be above the yellow line, and strictly above the yellow line and not touching the yellow line? So we're not going to include anything. Everything is going to be an open interval. So we're above the yellow line, as you clearly see right here. From here to there. This portion of the graph is definitely above the yellow line. We're above the yellow line from here to there. This portion of the graph is clearly above the yellow line. And where else are we above the yellow line? Well, obviously from here all the way to there. This portion of the graph is above, again, the yellow line. Well, what intervals are those? The one on the very far left, and I'll zoom out here, is from -infinity all the way to -1. I'm sorry, that's -3. That's a -3. We're above the x-axis from, in this little portion in the middle, from -1 to +2. And we are above that yellow line from +3 all the way to infinity. So there's your answer. And then the last part is when are we going to be greater than or equal to 1? So let me erase all of this. And we're now focused on the horizontal line of 1. When is the function going to be greater than 1? Well, greater than 0 is the x-axis. Okay, and this again is greater than 0. This is 0. 1 is going to be this one right here. So this question is asking us now, when are we going to be above this line that I'm highlighting in purple? Well, if we look at this graph right here, we're above this purple line from here to there. And we're also above that purple line from here to here. Again, this portion of the graph is clearly above that purple line. So our answer is going to be from not negative 10, but from negative infinity to the location of this vertical line, which is negative 3, and then from this vertical line, which is positive 3, all the way to infinity. And now, if you're asking, did Mr. Aviles make a mistake? And why is he talking about himself in third person? Is no, he did not make a mistake. Even though this right here has an equal sign, we are not going to use brackets here because this would mean that we would be touching that purple line at 1. And this graph, because this is a horizontal isotope, the graph never touches that purple line. So it's never going to intersect 1. So our interval is going to be open on these endpoints. And again, you can clearly see what's happening at 3. At 3, we're not touching that point. We're not touching the purple line at 3. The graph is moving away from that point right there. And the same thing at positive 3. The graph is moving away. We're not touching that value right there. And this end, obviously, this end is not going to touch because even though it looks like it's overlapping and it's on top, it's not. If with enough technology, with the right technology, we zoom in, we're always going to see that there's going to be a little gap, okay? A little gap. The gap is just getting smaller every single time we move further along the x-axis and make x extremely big. This gap again gets really, really small, and y just simply gets closer and closer to the value of 1 without actually ever equaling to 1. Okay, so we have no intersections. Now that concludes our notes for this topic, for topic 1.7. I'm sorry, 1.8, rational functions and zeros. If you have any questions, please send me a message through email or Parent Square. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.